Hello students, in this lecture we will discuss about the lossless join algorithm. As you know, whenever a relation is decomposed into the fragments like the R1, R2, R3, so we can check whether this decomposition is lossless or lossy type by using the primary key foreign key pairing, whether the fragments are able to generate the original relation or not. That already we have seen. This lossless join algorithm is another alternative to check whether the decomposition is lossless type or lossy type. Here we will not check whether the primary key foreign key pairings are existing or not. Here in a different ways we will check whether the decomposition is lossless type or lossy type. Let's see the algorithm. So I'm having a relation which is decomposed into the R1, R2, R3 like this. Let there is a functional dependency existing, that is the F. This lossless join algorithm performs certain steps to check whether the decomposition is lossless type or lossy type. So how to do? So here we will go for creating a table. In the table, we'll go for finding the different columns and rows depending upon the attributes and your number of relations respectively. So we are having 4 attributes. I can go for naming them are the A1, A2, A3, A4. This step is saying that construct a table with n columns, and that n is depending upon the number of columns. And the number of rows is depending upon the fragments. Like here I am having the R1, R2, R3 means 3 rows I can have R1, R2, R3. This is talking about your second step. So now the next sub steps are saying if one attribute is belonging to a relation, there we have to consider this one as the AI. AI means the small a with the respective subscript like A1, A2, A3, A4. If the column is not belonging to the particular relation, if it is not belonging to the particular relation, then there I have to go for representing that as the Bij. So Bij I can consider as the I as the column index and J as the row index. I can also go in other way also, row index, column index also. But in this slide I am discussing about the column index and the row index. But the alternative I can use. Then once I am creating this table with the respective AI or Bij, then I'll check every functional dependencies of the original functional dependency set. And I'll check whether the functional dependencies are existing or it is holding there. If it is not holding, I'll change the RHS part to make the functional dependency holds, because we know let the functional dependency x arrow y holds. That means if there are two instances, like if x1 arrow y1 and x2 arrow y2, let these two instances are holding, so there I can check if x1 is equal to x2, that implies the y1 has to be the y2. If same determinant I am having, the right hand side of the dependencies has to be the same one, because there only we can say the functional dependency is holding. If for the same x, if I am not finding the same y, I have to make them as the same y. How to do? If any one of the y is a and another one is the b, I have to go for converting the b into the ai. If both are the bij or bkj like that, so I have to convert them as a single bij or bkj. It depends. So in this way I'll check for all the functional dependencies. At the last I'll check whether any row of that particular table contains all the AIs or not. If it is containing all the AIs, the decomposition is called as lossless. Otherwise, the decomposition is a lossy type. So, in brief, if I'll say, I'll go for creating a table by specifying the rows and the columns. I'll fill them by using either the AI or Bij. After filling the AI and Bij in the respective cells, I'll go for checking whether the functional dependencies are holding or not. If that is not holding, I'll make it as the correct one. And after all, I'll go for checking whether any rows contains all the AI or not. If all are the AI, then I can say it is a lossless type. If none of the rows contains all the AIs, then I can say it is a lossy type. Let's directly jump to the different examples. Let in this case, there is a table called as R containing the XYZ. It is decomposed into the XY and X2, the YZ. And let the functional dependencies are XY, X to Y and Z to Y. So how many rows? How many columns? Very clear. I have to go for creating a table. I'm having 3 columns. So one is X, one is Y, one is Z. So I can rename as A1, A2, A3. I'm having two relations, that is R1 and R2. See, in R1, we are having the columns like XY. What will be filled there? Since X and Y are the part of the R1, I can go for putting them AI. So X means it is a capital AI, so I'll put small ai, that is A1. Y is the capital A2, so I'll put A2. In R2, the attributes will be YZ, so I'll put A2 and A3. Students, what I'll put in this Z of R1 and X of R2? I may go for considering the row column indexes or column row indexes, anything I can consider. If I'll consider the row column index, I'll put B, row is the 1, column is the 3. If I'll consider column row index, I have to consider as B31. But one approach we have to adopt. Similarly in R2, the X is not available, so I'll again go for filling that by using the B. So what is the row index? 2. What is the column index? That is 1. So this is the one table. Now I'll check for every functional dependencies. For X arrow Y. For X arrow Y, am I getting the same X? For X arrow Y, am I getting the same X? No. So if same X I'll get, then I'll check for the same Y or not. Since the X are not same, I'll not go for any change. So no change is required here. Similarly for Z arrow Y, is there any 2Z with the same values? No. So no change. So this table is not going to be changed by considering either the X arrow Y or Z arrow Y. Now you see the first row, is it containing all the AI? No. In R2, is it containing all the AI? No. So I can say, since none of the row contains all AI, my decomposition is lossy type of decomposition, right? Right, students? I'll see the other example where it will be lossless also. Let's see another example, just by changing the functional dependency a little bit. So here also there are 3 columns, X, Y, Z. I can rename as A1, A2, A3. How many rows? R1 is there, R2 is there. Students, like the similar to the previous example, R1 containing XY, so I can have the A1, I can have the A2. Similarly for R2, I can have the A2, I can have the A3. Here I can go for B13 or B31, so I may go for row column way, that is the B13 and B 2 1. So let's check for the functional dependency for x arrow y. Whether the two x are same, one is a1, one is b21, no. So I'll go for no change. You can check for y arrow z. So this is y, one value, that is a2, another value is a2. So two values of the y are same. Since it is a functional dependency, the z has to be the same one. You check, one is the a2 to b13, one is a2 to a3. So since the functional dependency is existing, that is y to z, so for the same y, the z value has to be the same. So out of these two z values, one is the a3, one is the b13. As per the rule, what should I do? The b has to be converted to the a3. That means here the table is changed. Change is required. So after doing the change, this b13 will be modified and it will be considered as a3. Right, student? So now check the R1. Is it containing all AIs? Yes, it contains all AI. So what I can derive from this? I can derive this is a lossless type of decomposition. Okay, students? Let's see another example also, which we have discussed in the previous content. That is, R is decomposed into R1, R2, and 3. No, here it is going for R1, R2. Here the number of columns will be little bit larger. That is X, Y, W, Z, P, Q. So I have to rename as A1, A2, A3, A4, A5, A6. There are two fragments, R1 and R2. So in R1, what are the columns? That is ZPQ. So go for that, A4, A5, A6. In R2, what are the columns? X, XY, so A1, A2, W is there, A3, PQ, that is A5, A6. So for R1, there is no XYW, so I can go for putting that by using the B index, B11, B12, B13. Similarly for R2, there is no Z, so I can go for B24. Let's check for every functional dependency. For XY, ROW. Students, check the XY combination. Any two XY combination, two occurrences are same? No. So I'll go for no change. Similarly for XW to P, so XW occurrences, one is B11, B13, another is A1, A3, so the occurrences are not same, so no change. So whenever they are same, then we'll check for the right hand side. For PQ to Z, we check one PQ to Z, PQ is A5, A5, another is A5, A5. So one is saying A5, A6 to the A4, that is the Z, another is saying the A5, A6 to the B24, because it is PQ to Z. Students, since this functional dependency is existing, since the same PQ is available for two occurrences, the occurrences of the Z has to be the same. One occurrence of Z is A4, another occurrence of Z is B24. So what I'll do here, this B24 will be converted to the A4, so that A5, A6 can generate the A4, right? So to maintain that, this B24 will be modified to the A4. So now students, you check in R2, I am finding all the AIs, right? So since I am finding all AIs, So what I can derive here? I can derive that this is a lossless type of decomposition. So now the question is whether I'll use this concept for checking whether the decomposition is lossless, or I'll go for the primary key foreign key pairing. So remember that if the number of fragments is lesser, I'll use the primary key foreign key pairing or this anyway. But when the number of fragments is more, very large, there the primary key foreign key pairing will take time, whereas this approach will give the decomposition is lossless or lossy type in a smaller time, right? Thank you.